Okay, for people who are joining this live stream today, we're going to try to talk a little bit about potential experimental implications of our models. And Jonathan has given a preamble saying that he doesn't do experiment. He does. He's not experimentally oriented. But I have assured him that I'm going to extract the information. So we'll see. So to me, there are two large domains. This is stuff we did last August, September, talking about this kind of thing. I mean, there are obviously two large domains. So, I mean, there are, maybe we should fill in actually first what we might call the theoretical predictions. And then we'll talk about the experimental ones. So theoretical predictions, the first thing is, reproduce general relativity. Right? That's one that's one sort of theoretical direction. And we think there's a check mark there. We think that's done. Jonathan, would you agree with that?
Well, there are obviously still many details to fill in, but I think we can be reasonably confident that we've got that in the bag, yeah.
So, but we don't have, I mean, yes, for the structure of the Einstein equations, but we don't necessarily know how matter, we don't know equations of state, we don't know other things about matter. But the interface between what's matter and what's the structure of space is still a little bit fuzzy. Is that a fair statement?
Well, I mean, that was kind of the understanding that better was the motivation for working on these kind of classical scalar field models, right? As a minimal matter field sort of Lagrangian. Yeah, not. I mean, that story is not yet completely filled in.
Right. So the probe of that as a scalar field is now one of the things that's a methodology that we've used in these theoretical things is scaffolding with existing stuff, like you're sprinkling on an existing solution and then removing the removing that underlying structure and letting it run purely purely using the underlying model, so to speak. Because that's an interesting, this idea of scaffolding it with something which is with actual sort of computations from general relativity, and then letting it free run is seems to be a reasonable approach. So, I mean,
another important kind of dynamical thing that we haven't I mean, again, we have a proof, but we haven't actually produced an explicit computational experiment of it yet, is looking at trajectories of test particles, which again is the motivation for working on those kind of topological soliton models as a way of testing that.
Right. So the test is a topological soliton as a faux particle. I mean, we don't know how faux it actually is.
Right. It might be realistic. It might not be realistic, but for relativistic purposes, it's just fine.
Right. Okay. Now, I mean, right. So, I mean, if we start listing kind of new phenomena, one class is early universe type stuff. And the main phenomenon there is, dimension change / inflation, and what the relationship between those two things is, which I don't think I don't think we don't have as good examples yet of dimension changing, of rules that lead to dimension change that, look like sort of the cool down of dimension, so to speak.
Well, it depends on what your initial conditions are. I mean, so the rules that, at least the rules that I've looked at that we know sort of obey the EFEs in the continuum limit, those will yield a dimension change if you start them off from an arbitrarily high dimensional initial condition.
So are you saying your 2-to-2 rules that you looked at in your recent paper will change dimension if they start with a very high dimensional initial condition?
Right.
Should we try it?
We can do, yeah.
Do I have the equipment to do so?
I guess. I mean, you have Wolfram model and you have my dimension estimators.
Okay. So okay, let's just try it. So let's see, where can I pick up one of your rules? Should I go to your paper, or can you put it in chat or something? Or
I can also put it in chat.
Yeah, that'd be the easiest thing to do probably. And then what we want to do, yeah, I really want to see this actually. This is going to be interesting. What will be your average kind of high dimensional? Well, I mean, we could just start off with a random graph, right? That's going to be, and then where are the dimension estimators?
Well, they're all in the function repository. I mean, Wolfram Hausdorff dimension is probably the easiest to use.
Okay, all right. Can it work on a graph, or does it work on a Wolfram model?
No, it works on graphs, directed or undirected. It will adapt accordingly.
That's very swank of it. Okay.
Resource function.
I'm totally confused here. Dimension estimator or just dimension?
Just dimension.
Crunch, crunch, crunch. What's it doing? Finding resource. Oops, didn't like that. Oh, we're opening it in 12.3. Well, who knows what that will do. Okay, but it didn't like that. Oh, there's a second parameter. There's a V. What is that?
That's a vertex. You compute the dimension at a vertex.
I see. Can I say all or not?
Yeah, you can. So if you say...
I'll just say vertex 1 to begin with. Eek. Okay, what did I do wrong?
Wait, is this a directed graph?
No.
Oh, wait, no, hang on. You have disconnected vertices, so the graph radius is infinite. So, okay, so the maximum geodesic ball radius, if you don't specify it, is taken to be the graph radius.
Okay, so I have to say...
But you have if you have a disconnected graph, so the graph radius is infinite.
All right, let's give it some more edges, and that probably won't be disconnected. Okay, so there, if I run these a bunch, oh gosh, okay, so let's see, how do I get the largest connected component?
If you just do connected components first, right? They're sorted by size.
I think it's connected graph component or graph connected components.
Well, connected components will just give you the vertices, but then you can call subgraph.
No, there's a way of doing that directly. Connected graph components gives you the actual graphs.
Okay.
Okay, dandy. All right. So then that's about that vertex. So I could just do I could make a table of like 20 of these, and I will get wow, that's surprisingly close. I'm surprised that they're so close for random graphs like this. Let's make a histogram of these. Hard to conclude much from that, but I'm surprised that this is let's just try just for fun. Oh, interesting. Oh, because it wasn't in the connected component.
Right.
Okay. All right. So these are clustered around dimension 3, which is really freaking weird. Oh, is that because the 600 is 3 times 200?
It's probably related, yeah.
Okay, so let's see what happens if I go up to 800 here. Fairly confusing.
Well, no, I mean, there's another peak around 4, which is kind of what you'd expect.
I don't know why there's a peak around 3, though. let's just go compute this. Oh, this is not set up to run on all my computers. It's only running on the local computer. Okay, so let's, I'm just curious. Wow, it's kind of weird. Great. Yeah, those are errors from parallel kernels. Okay, so a little bit of non-understanding there of what's going on. But let's see. Did you send me the a natural evolution rule?
Oh gosh, sorry. No, I was going to, and then you were. And yeah, by the way, if you want to compute, so there are various things you don't have to specify a vertex if you don't want to. You can say all and then comma and then property all dimensions, and that should return an association of all the dimensions. And then if you just want to return an average of all vertices, you can say vertex. You can use the option vertex method goes to mean.
Okay, in this.
Yes.
So if I say here, well, let's just do this for a start. And you say, instead of one, I say all, and then I say vertex method.
So all comma all dimension, you have to use the property all dimensions. Otherwise it'll get confused about what you're computing all of.
Vertex method goes to
mean.
Like that.
The average. Yep. Should work.
Okay. All right, so let's try this again for a table of, let's say, 1,000 of those. Let's make that a parallel table, even though it's not running on all my machines, but it'll be some at least. And let's make a histogram of that. It's a little weird because I wouldn't mind just having every single one of those dimensions from every, well, okay, let's just look at means.
Oh, you can have that too. You mean from every radius?
Yeah, I just have to say values, presumably.
So okay, so if you want to get the values for every radius, what you would do is say dimension, hang on, I think it's dimension method. Let me just double check.
Why is this so sharply peaked? This is really weird.
Interesting.
I mean, let's try a random graph with like 800 here. This is very odd. Don't understand this. I mean, we can try some other graph distributions.
But yeah, if you want to return all of the radii, you can, sorry, all of the dimension estimators for all of the intermediate radii, you can set dimension method goes to identity.
Okay.
Rather than
all the intermediate radii. What do you mean? As opposed to, you don't mean radii, you mean starting points.
Wait, hang on. What is it that you want to compute?
I wanted to compute the best estimate. Assume this is the whole universe. Assume this random graph is the whole universe. Give me the best average estimate of dimensions, starting looking at the growth rate of geodesic balls from every point in that graph.
Right.
Is that what this is computing?
Well, I don't know what you mean by best. It's computing an estimate, right? So
no, I understand that. I understand that. So
there's a whole collection of options, right? So one is dimension method, where you can say, you can specify whether you want to take a maximum, minimum, mean, or over all possible geodesic ball radii, or whether you just return the values for each possible geodesic ball radius.
No, I want it to take care of getting its favorite estimate given the growth rate as a function of ball radius. But I want it to do that.
Right. So right now it's taking. So right now it's taking the mean, because the dimension method is defaulting to mean, and it's also using, because you haven't specified a minimum or maximum radius, it's using 1 as the minimum radius and the graph radius as the maximum radius, which is possibly sensible, possibly not sensible.
Yeah, who knows? Okay.
Usually using graph radius as the maximum is not a great idea because you get dominated by boundary effects. But
well, let's see. I mean, okay. So anyway, we can analyze this, but let's try to take a look at. So you've got a rule here. This is a 4-2 to 4-2 type rule. And what you're saying is, if I take this random graph. So let's take one of these random graphs here. Okay, so here's our random graph. And let's say this is our init.
I'm not sure about a random graph because that doesn't, it's not obvious that has any, Riemannian manifold structure, but we can try it.
I understand that. But so then this rule, so we say resource function. Gosh, I don't use this as much as I should. It's embarrassing. Everybody else is using this, but I'm not. Okay, so let's try this rule, and we're going to try this initial condition, which I think we have to process into list triple at edge list of that init. Is that correct?
For Wolfram model, yeah.
Okay, and so let's say I say let's run it for 5 steps, and let's see, what do I want to do? That this is how do I make the plots for all the, how do I make the series of plots?
States plots list.
Boy, it's been surprisingly long since, is it states plots list or state plot list?
I think it's states plots list. I don't use Wolfram model either, but I think it's states plots list. Nope.
Wait a minute, what's wrong with this rule specification?
Wait, that arrow might not be the right kind of arrow.
I don't know what kind of arrow it would be, but let's try this. Help, what's happening? Okay, there we go. All right, so this is our universe, which is getting extremely spindly here.
And some pieces broke off.
Some pieces broke off, very unfortunate for anybody in those. Okay, so let's get a sense of what's happening here. So this is, and if we do the dimension estimator for these, let's just see what this is doing. Let's just try the obvious naive thing. Okay, so let's try, let's just try for 10 steps just to see what happens and see whether the universe is like disintegrating here. Wow, why is it running so slowly? Okay, so that, if we look at the largest connected component, okay, so that thing is becoming quite spindly. So its dimension is obviously going down because those fibers have lower dimension than the rest, than the main compact thing. So let's just take a look at what this is doing then. So let's say
that looks like it'll have limiting dimension 1, right? Because there's just a bunch.
I would think so. Yeah. So I mean here, let's say I guess states list, right? And then we're going to have to turn those states.
Yeah, just do an undirected edge at.
Well,
map.
a graph of undirected edge, triple at that, map it onto this, and that should give us the graph versions of all of these. Let's just check that it does. And then for each of those, we can then go and use your dimension estimator to get us the best yeah, we don't want to say 1, we want to say your all construction here. All dimensions, vertex, mean, whatever it is there. Okay, let's take a look at what this did. Okay, great, those are graphs. Okay, so now this is first of connected graph components of hash. Map that onto %26. Oh, what the heck, I'm going to do parallel map. I wonder, this is 12.3. I wonder if it's going to have its nice, let's see. No, it didn't. Okay. Okay. Well, it's a bit scratchy, but that seems to be dimension reduction, so to speak.
Right. And there's a much more robust test you can do that I briefly played with, but I want to look into in more detail, where instead of just starting from a random graph, you start from a graph sprinkled into a higher dimensional manifold, and you look at what happens to that. And that tends to those don't tend to disconnect, or they disconnect.
Well, we can look at that. Let's look at it sprinkled into. Let's just run this a little bit longer, just for fun. I mean, this may spindlify a lot. So here, let's run this for like 30 steps. It shouldn't do anything too terrible. And then let's run this on that. Wow, that was nice and fast. And then let's say list line plot of that. Huh. Well, fancy that. I wonder if that's because it did something trivial there. Let's take the first last of %29. Let's take the last like 3 of those. Oh, it's gone. It reached a stationary state. That's why it didn't go down anymore. You see what I'm saying? That's nothing's happening here. Jonathan, did we lose you?
No, I mean, yeah, obviously nothing's happened. Yeah.
Right. So, I mean, so what this is showing is this is decreasing the effective dimension and then flatlining because there's no activity. Okay, so let's just look. Can we try to do a sprinkle into a high dimensional hypersphere? Is that doable with your sprinkling functions?
Of course. Yeah. Like I said, that's the test I did to determine that this was a robust result.
Okay, so what is the sprinkling function of relevance?
Depends what you want to do. What kind of space do you want to sprinkle into? What kind of high dimensional space? I mean, the simplest.
How about a high? What's that?
The simplest would be flat manifold to graph.
Well, how about we just do a grid graph? Is that wait a minute? Sprinkling into a space. So I want a sphere, a ball in d dimensions.
If you specifically want a sphere, then you can do extrinsic curved manifold to graph, although that's slightly more complicated.
Well, I'm happy with a cuboid. Would you a rectangular parallelepiped in d dimensions? Is that easier?
Right, flat manifold to graph, as I say.
That's a function.
Yeah.
Okay. Well, I didn't know that. Okay, flat manifold to graph. Okay, dandy. So now.
So you specify the number of dimensions and then the number of points. And also you want to specify a cutoff radius, a discretization cutoff.
Okay, so let's say 5 dimensions and the number of points, let's say 100.
Okay, but as the intermediate argument, you probably want to, it'll default to using discretization cutoff of 1, which you probably don't want.
So what would I want?
I don't know. It depends how dense the thing you want. Yeah, how dense you want the thing to be. But like if you tried 0.2 or something, that might be more reasonable.
It doesn't look that reasonable. But what is manifold graph? What is that term?
That's too sparse.
How do I get just an ordinary graph out of this?
With or without coordinates?
Give me with coordinates to begin with.
Then you want spatial graph as the property of manifold graph.
Okay. Okay, that is not a very convincing 5-dimensional.
Right, that's way too sparse. So if you change 0.2 to 0.5 or something, let's see what happens.
What is that parameter again?
It's the discretization cutoff. So how close do 2 points have to be with respect to the Riemannian metric before you treat them as being adjacent?
I see. Okay, so this claims to be, I don't know why, it gave me an extra special luxury, 3D graph here, but I understand. This is attempting to be a 3D graph. This has to be an integer, right? You don't know how to do it outside of an integer, right?
We don't know how to do it outside of an integer. Unless otherwise specified, it will give a 3-dimensional projection if your dimension is over 3.
Why didn't it do that for 5 dimensions? Okay, so this claims to be something where there are points sprinkled into the volume of a 3-dimensional ball, correct? So, for example, if I were to look here at the vertex coordinates, how do I get out? I just say graph embedding.
You don't need to do that. If you just ask for points list, it will give you the coordinates.
Okay. All right.
I mean, actually, the points, the vertices are just the coordinates.
Well, I understand. Oh, I see. The actual vertex list would be the coordinates.
But yeah, if you just request points list, you're from the manifold object.
Okay, but I could also just say vertex list at %38, and I will get back the coordinates. Okay, fine. So then these, I would say, graphics 3D of point of this, and this is now an approximation to the contents of a sphere, right? That's the claim. Although
this is not a sphere. This is an approximation of the contents of a parallelepiped.
Okay, fine. So that is claimed to be uniform in that box.
Right.
So with all our fancy modern spatial statistics, we could even check that, but I'm sure you got it right.
Yeah, if you wanted to do a hypersphere, you could do extrinsic curved manifold to graph and then give the equation of a hypersphere. But it's
okay, as opposed to the computational geometry version of a ball, of some kind of ball of that. I mean, in other words, if I give a region, as in computational geometry region, can I sprinkle in that region? Oh, I see. The issue is that your point is the metric, if I just give a region, is still a Cartesian metric.
Right, exactly.
Metric.
Yes, right. This is okay. This is the only part of sprinkling that's slightly complicated. Is you have to care about the induced metric on the region that you specify.
Okay, fine. But let's take this guy, for example, and let's actually take the 5-dimensional analog of this. So what presumably will happen here. So spatial graph. Okay, so let's say I do 5 dimensions.
Yeah, in which case, okay, spatial graph may not work if you do. Okay, well, no, that's fine.
Okay, so it's giving a 2-dimensional. I mean, it's giving a 2-dimensional projection of that graph.
It's not even doing that. That's just the graph object. There's no. It's not coordinatized there.
Okay, all right, fine. I see, because it isn't very useful to give 5-dimensional coordinates.
Right.
Okay, so if I now go back to your estimator here, then the claim would be that this will come back with about 5 for that graph.
Right. It may not be quite. I mean, the radius may not be large enough for the dimension estimation to be very good, but
that says 3. There's distinctly not 3 is not 5. So let's try going up to more points, right? That would be the way that we would expect to get a better estimate. What is it doing here? Is this parallelizable, what it's doing right now?
Probably with a bit of effort.
Okay, so it's spending lots of effort here.
Right. I mean, bear in mind, it's going to have to do. It has to do, pointwise comparisons between these things, so that this scaling is not linear.
Why does it have to do pointwise comparisons? Why is it not using the nearest function or something?
It is, but the nearest function only gets you. I mean, it's using that to essentially tell you the neighborhood.
Okay. So do you know whether any of the new spatial statistics functions could be used for any of this?
Almost certainly, but I haven't reviewed them in enough detail to
know. Because what you're looking for here is nearest neighbor G. The prop is that not what is that what you're looking for here?
Not exactly. It's related, but it's not exactly that.
Okay. Can you say, I mean, because we can histogram of the point density function. Anyway, I think it'd be worth asking somebody from that group whether they can see how to dramatically speed up what's going on, because they just implemented this stuff with great effort. There's our graph. Okay, let's take a look, see whether it did better here.
Right. I mean, but like I say, the problem is not just the number of points, it's also that the graph radius here is going to be very small.
Yes, I understand.
Which you can actually, which you could fix by reducing the discretization scale. Okay, well, it's getting bigger.
It's getting bigger, right? But let's look at your thing when it isn't mean. Can we look at it for all? What's the way of getting it for all radii?
For all radii or for all points?
Both.
Okay, so if you want all vertices, you say vertex method goes to identity.
Well, actually, I'm happy to average over the vertices, but I want to see it as a function of radius.
Okay, so in that case, you want dimension method goes to identity.
Oh yeah, that's a nice way to do it. Nice design. Oh. Okay, so this should give us the effect, the estimated. Oh, nice. Okay, fine.
So right, as expected, the
It has graph
boundary
radius
effect.
3. Right.
Right. And at radius 3, the boundary effects drag it down.
Right. Okay. Although the universe, I mean, okay. So now let's look at, so this thing, if we were to take it, percent 43, I don't know if this will be too slow, but it might not be. Percent 43, let's have that as our candidate universe, and let's actually evolve it with this rule. Okay. That's percent 43 there. You know, it'll be really nice when we modernize this whole percent business and make that less grotesque. Okay, let's try running this. Okay, and then let's, for these, I have this bad feeling it's going to be quite slow to render those things, but maybe for the dimension estimation, it won't be so bad. So let's take a look using this. For each of those. We're waiting for the very first 10 to the minus 200 seconds in the evolution of the universe, and it's taking an awfully long time. How depressing. Fortunately, we have things like general relativity to give us a way to jump forward. Okay. But
it's
what we go ahead.
Good that the beginning of the universe is slightly computationally non-trivial, because it indicates that sort of there is something to inflation.
Maybe. I mean, let's see. Okay, well, we'll keep that running. Okay, but let's talk a little bit about what this all means. So one question, go ahead.
This dimension cooldown effect shouldn't be surprising, right? Because it's predicted by our general relativity derivation. If it were the case that this rule did not lead to a converged low dimension, then it would not obey the Einstein field equations, because the way that the Einstein Hilbert action is extracted is by saying that effectively there is a convergence of the dimension to some fixed value.
Yes, I agree. But what is that fixed value for this rule? Do we know?
It was close enough to 3+1 that it was usable for practical simulations, but I have no idea if it's exactly. I would be surprised if it's exactly 3+1.
Mm-hmm. But so that's an interesting question in its own right, is what the equilibrium dimension is for one of these rules that has, which, I mean, this rule is generating, let's see, it's the number of vertices here can increase, right?
No, it can't. This is a pure permutation rule.
Well, okay, it's not generating any more atoms.
The number of hyperedges can increase. The number of vertices can't.
Wait a minute. It's got a U here, which does not appear on the left-hand side. So I think it's the other way around. The number of hyperedges can't increase, but the number of atoms can change. I'm a little confused here because the Z does not appear on the right-hand side. Right?
Right. It's removing a vertex and it's
adding a vertex. It's removing one and adding one.
Right.
So the net number of vertices should stay about the same, and the net number of hyperedges should stay about the same. But the connectivity may change, which changes the effective dimension.
Right, exactly. Yeah, sorry, it's not quite, it's not exactly a pure permutation, but it doesn't change the number of vertices.
On average. I mean, it might, for a particular configuration, it might change. The number
only in weird cases where you have degeneracies between, input vertices and things.
Right. Although I don't know how weird that really is. But in any case, okay. Well, we're still running this. Okay. But so one question is, okay, from the beginning of the universe, this happens, it gradually, so one of the questions would be, in a situation like this, what is the effective field theory, essentially, of the cool down? So in other words, if we took dimension as a dynamical parameter, would this thing look like, what would it look like? What would the typical dimension cool down be? And how do we estimate that? How do we get, because, when that's actually a good question. What is the effective equation for the dimension? How do we think about that?
Right. Well, I suspect, like with inflation, like the fact that there's, there are all kinds of ways to parameterize inflatons, right? There's like slow roll, there's K inflation, there's, various parameterizations. I suspect the same would be true of dimension, that there are probably many possible effective theories of dimension phase change.
Well, it is not a phase change. It's a continuous change here. Almost
I would
certainly.
argue, sorry?
Almost certainly it's a continuous change, I would think.
Why? I mean, because the
you think there's some percolation effect where the thing has, okay, so that's a good question. Is the dimension cool down continuous, or does it have phase changes? And that might be, if there's a phase change might be like something like percolation. But let's see how we would think about. I mean, so okay, if we want to estimate, so we're estimating dimension. Dimension is the growth rate of geodesic balls. As you're just sort of messing around with the system, how should dimension change? If this was density, if we had coordinates and we were asking about density, we would expect the diffusion equation to be the thing that determines the change, right? So the diffusion equation, how do we derive the diffusion equation? When they're just a bunch of particles bouncing around in a fixed dimensional space, we derive the diffusion equation by saying each particle random walks to a different place, and the result will be the diffusion equation. Does that make sense? So what's the analog of that for this case as we think about dimension changes? We think about these geodesic balls. Can we think about, we got a geodesic ball and essentially atoms are being exchanged between geodesic balls. Is that a reasonable picture? And if so, so we have a geodesic ball which has a certain growth rate. It has a certain number of, the atoms. There's sort of a layering of increasing numbers of atoms as we go out in the geodesic ball. As those atoms are being randomly reconnected, what happens? Okay, so here's the question. If we did random reconnection, what would happen to the dimension? Just ignore the rule. Just randomly reconnect. So we have a graph, and we ask, so don't even worry about whether it's local. What would that effect have? I mean, actually, if it's random reconnection, my guess is if it's not local, my guess is what you would end up with is something much more like this, a higher dimensional thing. If it's completely random, the dimension can increase. Why does the dimension, give the argument for why the dimension decreases? Okay, can you give the argument for why the dimension decreases with this rule?
Well, because it obeys the Einstein Hilbert, it extremizes the Einstein Hilbert action.
Yeah. Okay, let's try again though, because let's see if there's an intuitive way to understand why that would reduce the dimension. I think we need to plot what this rule actually does.
What's not intuitive? I mean, it's literally the statement. I don't.
What do you mean? But that requires, I understand, but that requires the whole apparatus of the things that we've built to talk about it in terms of Einstein Hilbert action and so on.
What things that we've built?
Look, to define that notion, you have to define a notion of space. You have to define all kinds of things. Whereas
you have to define a Lorentzian volume measure, which you would have to define, which you have to introduce to define dimension anyway. And you have to be able to take the second order term in its Taylor expansion. There's no other apparatus.
Okay, I claim there's a simpler way to understand this. I claim there's a way to understand this that's just a little story of graph theory. And maybe I'm wrong. In other words, I claim there's a way to understand it in which we will get an effective equation. And the main payoff for that would be that we will get an effective equation. Let's see, what do I want to say? I want to say of model rule, of model there. And then I want to say rule plot of that, don't I?
I completely don't understand this.
Okay, don't understand which.
Your statement that, so what does it mean for dimension to converge to something finite, right? Well, it means that it doesn't grow.
Yes.
What does it mean for the dimension not to grow? Well, it means that the Lorentzian volume measure grows like an exponential with a constant exponent. Or in other words, the higher order terms in the Taylor expansion go to zero.
Yes.
Which is the statement that the Einstein Hilbert action is extremized.
Yes.
I don't see how that could possibly, it's literally the definition of what it means for the dimension to converge. I don't see how it could be simpler than that.
I still think there's something simpler. In other words, what I'm claiming is
simpler than what, though?
Okay, but so first question is, this is a local rule. Okay.
You think there's a simpler definition of dimension?
No, I don't. I think there's a way to understand. Okay. When you say it goes towards, okay, so let's take what you're saying. Okay. It's extremizing. What it's doing is it's doing the analog of finding a minimum where the Einstein Hilbert action is extremized, right? Okay. So let's imagine that process. Okay. Maybe that's the way to think about it. That's a process extremizing the Einstein Hilbert action. And it's not, I think I'm going to have to kill this, and that, okay. So one thing is to just say it's extremized, therefore it satisfies the Einstein field equations. But now the question is, how does it get to that extremal value? Right. So in other words, because that's one way. If it's going to satisfy the Einstein equations,
how could that possibly be simpler? Because that's going to be a highly complicated, rule-dependent thing about which we can make no general statements, presumably.
I don't know. So okay. So there's two possibilities here. Okay. In thermodynamics, for example, you can make statements in equilibrium, but you can make a limited number of first-order statements out of equilibrium. Right. So if it is the case that this dimension cool down is an approach to equilibrium, okay, which it might very well be. If that's the way to think about it, that's an approach to equilibrium, then there's the possibility that these sort of first order dissipation theories might apply. And then we might be able to have an effective theory that gives us something like a diffusion equation or something like that. In other words, here's my question. What do we expect the function as a function of time, dimension as a function of time in the early universe to look like?
Right. And as I said, and as I discussed at length in the first relativity paper, there's strong reason to believe that it is at least as unconstrained as models of inflation.
Okay.
I defined a minimal scalar field theory for dimension change and showed that you could obtain arbitrary conformal structures within the context of a VSL model, which means that it's probably at least as unconstrained as inflation.
Okay, so let's. Okay, that's interesting. Shall I pull up your paper? Is that a useful thing to look at here?
I don't know. I'm not sure what the question is.
I'm trying to understand whether, so your statement is, okay, so is dimension cooldown an approach to equilibrium phenomenon that does not show sort of, I don't know what the right term is, universal behavior? That is your assertion, is that that's the case. Now, I would say, based on the analogy with thermodynamics, in thermodynamics, the first order dissipation functions do have some degree of universality, not as much as the full second law story, but that's the whole, the fluctuation dissipation theorem and all these kinds of things are a way of computing the first order things like thermal conductivity and so on, which are the first order deviations from equilibrium. And so in this case, so what we're expecting here, and maybe you already worked it out, I don't know, is something, I would expect something beyond the Einstein equations, that is the first order deviation from equilibrium, that is the dimension cooldown, that is the end of dimension cooldown, so to speak. Now, maybe you already worked that out. Do you think you did, or what?
I worked out the form of it because it's trivial. You just take the Taylor expansion, but it's not I don't think there's anything deep there.
Okay, which section do we go to?
There's a section at the end about cosmological implications of changing dimension.
Boy, you have a lot of references. Good for you. Okay.
Right. So that thing you skimmed over there was a minimal phase change model of.
Okay. All right.
Dimension. So,
which thing I skimmed over? So the thing further down here?
Right. This is just setting up how to think about dimension change.
Okay. In terms of what? In terms of a Cayley graph of, okay. And
no,
you're saying
in terms of a generalization of a topological manifold in which dimension is not a local invariant, analogous to how it isn't in the continuum limit of a beta lattice.
Wait a minute, a beta lattice has infinite dimension, doesn't it?
Right, but locally it can have finite.
How far can it go? I mean, its geodesic ball is going to grow exponentially, isn't it?
Yeah, but that's for a global effect, right? A local effect when the geodesic ball has a bounded radius. That's what it means to be local.
Okay, fine. Okay, so now, is this where you're talking about this?
Right. So you parameterize dimension change as a variable speed of light, which is kind of the obvious, easiest way of doing that.
Okay, let me think about that for a second. Okay, so you're saying the way to think about this, because that's relevant for, okay, that's also relevant for looking at the phenomenology of things, is, okay, why is that right? Why is that right? I don't quite understand that. I mean, so the volume that you get to in a certain amount of time, the spatial volume that you reach is determined both by this, is determined either by the dimension, as in r to the d, or it's determined by the speed of light. But the speed of light is a constant in front of, so I'm a little bit confused here. Can you explain this?
The speed of light is a constant in front of what?
Well, in front of the r to the d. So I mean, in other words, if you're going to ask the question, how many?
The speed of light has nothing to do with the expansion parameters in the Riemannian volume element. Riemannian manifolds don't have a speed of light.
I understand, but okay, given that you start at a particular point, after time t, you're going to have gone, you know, c times t, a distance c times t, and so the volume of that is given by this volume element. But so I don't understand the distance that you go. I'm confused here. Can you explain? Okay, so I understand if you have a variable speed of light, I understand how this goes through. But can you explain? Okay, let's start with something very naive here. Okay, so relationship to okay. Can we go through this extremely naive thing? So I've got some. Let's take I've got something. It has a certain dimension. No, I'm not understanding this. Can you explain how do I understand the relationship?
What am I? You keep asking me to explain something, but I don't know what I'm explaining. What
relationship between variable speed of light and dimension change?
I don't understand. So what an increased, a hypergraph that's approximating a Riemannian manifold with a with a locally increased dimension has higher causal connectivity. That's what it means.
I agree with that. I agree with that statement. Yes, and the causal connectivity increases by as the dimension changes. The connectivity increases. If the dimension is d, the number of nodes reached goes up like r to the d. Right? The effective number of nodes inside the causal cone goes up like r to the d. Right? So the thing I'm confused by is on the one side we have r to the d. On the other side we have c times t. Those are the two things that are ways of estimating how much stuff there is in the causal cone.
Yes.
Okay. So what I'm trying to understand is we fix t, and you would say, so as we change d, you're saying that can be emulated by changing c here.
Yeah.
Right? Okay, fine. So wait a minute. Actually, the correct thing here is this is why I'm confused. This thing is more like t to the d, isn't it? No, it's not.
Well, this is the thing. I don't understand what it is you're talking. Are you talking about the Riemannian volume element? Or are you talking about the Lorentzian volume element?
Well, perhaps that's where I'm confused. I mean, what I'm trying to understand is I'm trying to get a sense. So you start some effect and you generate this causal cone, and it involves, okay, if we imagine something, I mean, I had some pictures of this. Hold on. Let me find it. Here we go. All right, so I had, okay, so here, I don't completely remember exactly what this picture is of, but basically this is showing in successive ticks, so to speak, this is showing what part of the reconstructed spatial hypergraph can be affected by some event at a particular node. Does that make sense? So what you're saying is, I can imagine the way that effect grows, either in terms of dimension change, either in terms of being in a different dimension or variable speed of light. Is that the claim?
It's not variable speed of light.
It's a different speed of light.
The point is, in the expansion, in the standard Taylor expansion for the Lorentzian volume element, the radius of a cone projected in a particular direction, from which you then compute, the Ricci curvature tensor and things like that, its radius is dependent on essentially the conformal scale factor. It is dependent on what would be a generalized speed of light, right?
Yes, the projected thing. So given the causal cone, right, projecting a causal cone onto an instantaneous, to an instantaneous spatial hypergraph or something, to an instantaneous spatial structure.
You don't have to project it onto onto anything of codimension 1. You can project it onto a codimension 0 manifold.
Really? I mean, look, you project this causal cone.
The conformal structure is defined at the level of the Lorentzian manifold, not at the level of the Riemannian manifold.
You're just saying that the actual volume of the causal cone, as in the number of nodes in the number of events in the causal cone, right, which is it's some measure of its volume, the number of events in the causal cone, which is the thing you're describing here, the number, okay, events in the causal cone is something like...
I was trying to make sure that we agreed on the continuum geometry before I started talking about the discretization of it.
Well, it's easier for me to understand the discretized version.
Okay.
I mean, so the number of events in the causal cone, you're saying, is approximated by essentially C times, actually it's more than that, it's C, if I'm not mistaken, it's CT to the, depending on how you do the dimension, D times this. That's the number of events. Is that true?
Well, that's asymptotically, yes.
Right. So because that's the sort of spatial expansion and that's the temporal part.
Well, one determines the radius, one determines the length.
Yes. Right. Of the height of the causal cone. Right. Okay. So now what you're saying is, if I change D, see, this is the part I'm not understanding. If I change D, you're saying that I can compensate for that by changing this multiplier C. Is that correct?
Right. If I increase D beyond what it actually is, so to speak, I could simulate that. Okay, suppose you have a, I don't know, 3-dimensional or 3+1 dimensional limiting causal graph or something.
Mm-hmm.
And you want to pretend that it's actually 4+1 dimensional. One can compensate for that by essentially having C increase over time. Right?
That's not obvious to me. I don't understand. Given a particular time origin, but that's not true time invariantly. If you do time translations, you will not get the same result. In other words, if C, okay, if you start from T equals 0.
What do you mean? You just have to assume that the function that, I mean, as I do in the paper, that the function defining C is covariant.
Okay, but what you're saying is,
equation is covariant.
What's that?
All the other quantities we're dealing with are covariant, so I don't see why that one wouldn't be.
Okay, let's try this again. So this thing here, in order to get the same, okay, so you've given the example, C times T to the 4th or something, times T, whatever. And that is to be simulated. So we've got C of T here, right?
Look, I don't see why this is complicated. So, okay, you have a function, a times x to the n, and you want to, so obviously asymptotically it scales like x to the n if a is constant. Yep. You want to pretend that it's you want to pretend that it scales like x to the n plus 1.
I understand. So if a
equal x, then it's done, right? So
I know. I get it. I get it.
Yeah. Okay. So
I don't understand your statement. Okay, I understand that if you start at t equals 0, you can, by changing the speed of light, you can effectively make this cone right? You can sculpt the cone to be any shape you want by changing the speed of light as a function of time. Given that you start from a particular event, right? If the speed of light starting from, if the effective speed of light when you start from a particular value of t changes from what it is at that t0, then I see that you can do this.
Right. But it doesn't depend. It's a covariant quantity, because if I translate, in that simple example, if I translate x by some arbitrary, additive, I can I can introduce any arbitrary additive constant, and the asymptotic scaling is unaffected.
Okay, let me understand that claim. So the claim is that if C of t
will be affected, it's still going to grow. The higher order term is not affected by an additive constant.
I understand that point. But what you're saying then is C of t. What you're saying is if the speed of light increases, let's say linearly with time, okay, then it doesn't really matter if the starting point is this or that. But it requires, when you say variable speed of light, my initial sort of impression is, oh, that means the speed of light is varying by 5% or something. But that's not what you're talking about. You're talking about the speed of light varies so dramatically that it can overcome a change in the exponent of the volume of this causal cone, and that's fine.
Right.
But I hadn't.
If this effect occurred physically, then it must have occurred over a relatively short time scale. So a dramatic change in C is not so bad.
All right, fair enough. Okay, but so this is a way of thinking about how to parameterize that in a Friedman-Robertson-Walker type setting.
Right, exactly.
Okay, I finally understand. Okay, I get it.
The basic point is that the mathematical apparatus for analyzing, variable dimension doesn't yet exist, but the apparatus for analyzing the variable speed of light does. And the point is, one can translate problems in one setting to a problem in the other setting.
All right, okay, so I get it now. Okay, so let me rephrase both my confusion and what I've now understood. Okay. So what you're saying is, by having the speed of light change with time by some power of the time, that power of the time is, if C goes like t to the alpha, then that alpha is the essential correction to the dimension, so to speak. And so then the claim would be, if you allow alpha itself to vary with time, then that is potentially able to model, in other words, if the end result is going to be, spatial dimension 3 or something, then you can parameterize the deviation from that by having an alpha, which, for example, goes to 0. Once it's 0, you have sort of the basic dimension of the space. And when it's non-zero, you have this correction because you're essentially gulping in more space because the speed of light is increasing.
Right. So for if you want your limiting universe to have a constant speed of light and a constant dimension, which we do, then it has to, then effectively your speed of light has to be dominated by a term of order t to the alpha, where alpha is the dimension anomaly.
Okay, but the claim would be that then the speed of light, it's a little bit weird, because as we go back to t equals 0, we're saying that the speed of light is always increasing, because it always has to, in order to have higher dimension than the basic model, so to speak, the speed of light has to be something that increases rapidly with time. It increases as a power of time, does it not?
If the speed of But the rate of increase decreases.
All right. So what we're imagining is that at t equals 0, so let's say that at t equals 0, the speed of light is increasing exponentially with time. And
that is, if you want the effective dimension to be more than 1 higher than the true dimension. If it's less than 1 higher, then it decreases with time.
Well, if it's less than 1 higher, then okay. The point is t to the alpha, speed of light has to go up like t to the alpha in order to have an effective dimension of d plus alpha, so to speak, where d is the basic dimension of the system, right?
Right. So if you want the dimension to be less than 1 higher, alpha is less than 1, which means that the speed of light decreases with time, not increases, as you said. So the point is, what happens, assuming that assuming the model that I was assuming in this paper, where you start in effectively infinite dimensions, you get a rapidly increasing speed of light, which then decreases after alpha drops below 1, and eventually alpha converges to 0, which is when you get a fixed finite number of dimensions with a fixed finite speed of light.
Okay, let's try this again for a second.
The
Okay.
formal structure of that universe turns out to be sufficient to solve, horizon and flatness problems and things.
Okay, so let's understand that for a second. So you're saying that in the anomaly, if it's t to the alpha, if the speed of light goes like t to the alpha, the effective dimension is d plus alpha, right? That's the claim.
No. Wait. You say t plus alpha.
I said d dimension.
D plus alpha. If
speed of light goes like,
as always with these conversations, I'm very confused about whether we're talking about Riemannian or Lorentzian spaces, but whatever d means.
Okay, yeah, I understand. There's a +1, etc., etc., etc. If c goes like, then dimension is d, whatever d is, plus alpha, right? Okay, so your claim is that, and this, it may matter whether we're talking about this Lorentzian versus Riemannian story here, because your C, I'm very confused by your claim that if alpha is less than 1, that corresponds to, boy, I don't understand that. How should I intuitively understand that? That if the speed of light is decreasing with time, look, if the speed of light is a constant, the dimension is d. If the speed of light is increasing with time, no. Wait a minute. I'm very confused here. Wait a minute. What are you saying? I mean, the speed of light, let's say the speed of light is square root of time, okay? I mean, just to be very naive about it, this still, oh, Puffle, we're still running that previous thing. I think we're going to have to kill it.
Yeah, it's still, obviously, t to the 1/2 still increases. It's a question of what is the second derivative doing?
Okay, and why do we care about the second derivative?
I don't know. I mean, I assumed we cared about the dynamics, but maybe we don't.
Well, because you're claiming that the effective in Friedman-Robertson-Walker, the effective the a double dot obeys some equation, which you probably have written down somewhere here. Maybe that's the equation there, right?
Right.
Okay, so you're saying, given that we have C of t is t to the alpha, then you can figure out what a double dot, what the dynamics of a of t is. Okay, and so I'm assuming you've done that here.
Mm-hmm.
And the answer is?
So there's the a double dot differential equation for arbitrary n.
Where n is what we were calling alpha before, is that right?
Well, no, n is the d plus alpha.
Okay, nice. All right, okay, I get it. Let me kill this stupid thing. Sorry, this has been held up.
You just destroyed a whole universe.
I just destroyed a universe just as it was getting going. So sad. Isn't it lucky that every mathematical universe is somehow equivalent to this? Okay, in any case, this is, okay, so you're saying this is if n is equal to d plus alpha, then that, you claim, is the equation. These are the two. No, you don't need both of them. You only need one of them, don't you?
No, you do need both.
Okay, then these claim to be the equations for okay.
Right.
So that in fact in my quest to get d-dimensional physics, right, this would be an example of something that should be on my list of the d-dimensional Robertson-Walker. And
right. You'll notice that I wimped out by not having the d-dimensional Einstein constant.
what do you mean? You just have G sub n, which is some weird thing with weird dimensions.
Right, exactly. I didn't bother to work out exactly what that was.
Well, it's not. It isn't anything. It's because it has different dimensions from the usual one. There is no working it out because you can't compute. It is a different. You can compute it in a model, but I don't think you can compute it in the abstract. I mean, I gave in that technical introduction thing of mine, I gave the exponents and things that this depends on, for what it's worth. But here, the dynamics of n, I'm not understanding. Why is there no this here doesn't have n dot? Why not? Does the equation really not depend on n dot?
No, except insofar as a dot and a double dot depend on n dot.
But so the statement of the equation itself. So let me just try to understand this equation for a second, okay? Just so I'm convinced about how this all works. So, okay, so the speed of light, where do we get the where does the speed of light enter? That's the Hubble constant, Hubble distance. Okay, where is, okay, so someplace here we have C of t. Okay, this is the line element, which has a C of t here. Okay, I get it. Now what happens? So then you substitute for C of t. C of t equals t to the, d minus n or something, n minus d. Is that right?
Right.
Where does that happen here?
Well, it's not explicitly written out. I mean, it's just
okay. But someplace you define n. Okay, so here we've got this C is really C of t. Am I correct?
Mm-hmm.
The Hubble the Hubble parameter, the size of the universe parameter, is, well, that's not really the size. The A is the okay.
Factor.
Right. Remind me of the relationship between A and H.
Well, I mean, this is the relationship between A and H.
Okay. And K is the 0 minus 1 plus 1. Is that right? K is the whatever.
So H is defined to be the ratio of the expansion rate to the expansion parameter. That's what the Hubble parameter is.
Oh, here we go. No, yes, is A dot over A. Yep, okay, fine. Yeah, I get it. Okay. Assuming, okay. So wait a minute. Speed of light decreases from C0 to C sub m. Okay, so here we've got, what is epsilon?
Epsilon is the number of e-folds of this effective inflation.
So wait a minute. So if it was the case that it's lambda dominated, right? Then the differential equation, which should be somewhere here, the differential equation for A dot is such that A is proportional to, I mean, then there should be an exponential dependence of A of t on t.
The point is, for radiation dominated universes, the most generic solution appears to be one in which the alpha is negative, right? In which the effective dimension is lower than the true dimension, whereas for matter dominated universes, it's in general positive.
But what if it's cosmological constant dominated?
then it's kind of unclear.
But aren't we assuming that in our setup? I mean, I would assume. Well, I would have assumed that the cosmological constant was quite dominant in the early. I mean, it's a little bit unclear because we have to set the zero of energy in our models. Is the cosmological constant determines the zero of energy, and
well, there's also the point that it's not entirely clear how lambda scales with dimension.
Let's talk about that for a second, okay? Because I think that is somewhat. I mean, so lambda. What are the normal dimensions of lambda? It's an energy density, isn't it?
Right, exactly.
Okay. So lambda in our kind of models, let's see. In our models, the flux of causal edges determines energy. Well, the flux through a given area, through a given region, is the energy in that region. So unfortunately, it's a little bit difficult to define what it means, what a volume element means in that case. But essentially what we're saying is it is the, let's see, it's the energy density. I mean, I kind of think that lambda is going to wind up simply being some kind of ratio between the number of events and essentially the number of atoms of space. That is, it's something like the per. Let's see, how does this work?
I don't understand. Isn't that just the definition?
Of what?
Of lambda. It's the ratio of the events involved in maintaining background space to the events involved in maintaining baryonic matter terms. Isn't that how we're defining it?
It is, but I'm trying to understand that. I'm trying to understand whether there is a maybe. I mean, I mean, your point there is this. Okay, let me unravel that point. Okay, your point is the scale of energy is determined by things that we detect in the universe, which is the difference between sort of, it's the, insofar as there's actual matter of the kind that we think of as matter, baryonic radiation doesn't matter, but matter as opposed to the maintenance of space. What you're saying is our definition of an energy scale depends on things happening in that kind of zone above the activity that's associated with maintaining the structure of space. So when we define an energy scale, what does 1 joule mean? We're talking about it in that, with respect to that.
Well, I'm asking. That's what I'd been assuming, but
I think that's correct. But then, if we want to write the cosmological constant as such and such a number of joules per cubic meter, right? Then we need a definition of a joule, which depends on. I guess that's right. Okay, so then. Okay. So fine. Let's come back here to looking at. So what happened in the oh boy, how does this work? I mean, the question of how much frothing there is in the early universe versus how much just pure maintenance of space there is in the early universe, I don't think we can answer. My guess would be that the relationship that if in the current universe, frothing, which is everything we care about in the universe, might be 1 part in 10 to the 120, let's say. My guess is in the early universe that fraction was much larger.
The point I was making about we don't know how lambda scales was simply that maybe it's a trivial point, but ordinarily this separation of events involved in baryonic matter maintenance. I'm okay, but within baryonic matter, let's include radiation.
But you shouldn't say baryonic matter. Let's just say matter, because matter is not space.
Right. I'm using the cosmology, the cosmologist's definition of baryonic.
I know. Yeah.
But yeah, okay, fine. Everything that isn't, everything that isn't the pure Einstein Hilbert term in the relativistic Lagrangian density, let's treat as being matter. So normally you can make that separation because every event is involved either in maintaining the background structure of space, which basically means maintaining the number of dimensions, or propagating these matter terms, matter fields. But when you have dynamic dimension, there are also events that are involved in neither of these things, that are involved in modifying the dimension, right? They're actually destroying the structure of space in some sense, right? They're removing dimensions, and they're not involved in propagating matter fields. And so the question is, in that situation, how do you define the cosmological constant? How do you define energy scales?
Right, because you're saying that matter. Okay, so to what extent? Okay, so the claim is cosmological constant.
The point that I'm making is, unless I'm missing something, there is effectively a third form of contribution to the stress energy tensor that occurs during.
Yeah, I agree. Yes, I agree, and it is associated with the dynamics of dimension. Right. It is a correction to the normal equation of state in some sense for matter, in quotes, because it isn't matter and it's not an equation of state. But other than that, but okay, so I mean, the cosmological constant is roughly associated with the events associated with matter. Is this the right way up? Events associated with maintenance of space. No, it's the other way up.
Right.
Okay. So, which is why in the most naive version of this, it's a little different from this, because the most naive version in our models, it's kind of interesting, and I haven't really understood this, that the 10 to the 120, maybe it's just coincidence, that we get in our rough estimate of elementary scales is kind of comparable to what people often quote in the cosmological constant as found in quantum field theory. And I don't know if that's coincidental or not. Suspect not. Suspect it's because there are only a limited number of scales and it's basically dimensional analysis. But okay, so you're saying, I mean, if we look at it in the Friedman,
there's also a slightly ad hoc point, which is that there's a lot of room to sequester the standard model vacuum energy below the electron scale.
What? Say that again. I didn't understand that.
This the 10 to the 120 over prediction of vacuum energy from the standard model calculation.
Yes.
Right? One could imagine that being effectively sequestered at scales that are below the curvature scale that would be required. Okay, in order for you to have the sort of vacuum catastrophe, the standard model vacuum energy has to be present at scales that are sort of geometrically significant. Right. In order for you to get pushed over the critical density and everything.
Yes, but I mean, I think none of this stuff is relevant in our models, because in our models, that quotes vacuum energy, which is basically activity in the maintenance of space, is also what makes space. So you don't have this issue of, I mean, I think this is a non-issue, but let's go back to the more interesting question.
That's just the definition of what vacuum energy is. I don't know, whatever. Maybe it's a stupid point.
I think I understand your point. I'm not sure it's, we can unpack it, but I think the more interesting thing here is to look at Friedman, Robertson, Walker and ask what I think you've done here, which is what the effective Friedman, Robertson, Walker equations are in the case where there is variable dimension. Okay, so that's what your equation here is, I was just trying to understand the derivation of that equation, right? So you're saying this is the effective solution. So these guys, you're saying, had looked at C of t goes like t to the n. Is that correct?
Well, no, they had just looked at arbitrary values of c. What I'm doing is coming at it from the other direction and saying, if we let n be variable, then from that we can extrapolate our dynamics for c, and the solution we get for the scale factor is the same when we do the appropriate conversion as the Hollander Pareto solution.
Okay, hold on. Let me walk through that for a second. So in this equation, so what is the equation which still has c of t in it? Because this is now the logarithm of c, right? I mean, this n is assumed c goes like t to the n. Right? So that's the logarithm of c here. So what's the version of this equation that still has c in it? Is that the thing up here?
Well, you just take an exponent. I mean,
I know, but I just want to see the derivation, because the equation has, wherever you had the volume element, the line element, right? This line element, I think I understand. This line element, I'm convinced about this line element. Okay, so now we have to go from that line element down to the reduced description with a of t, which I believe is just the fr whatever, how many l whatever it was, the thing that used to be called FRW or something. Okay, is the assumption of the spherical symmetry plus that, then that gives us a single scale parameter, correct?
Well, spatial homogeneity and rotational symmetry.
Yes. Okay, so fine. So we should have an equation which the only thing it depends on is this line element, which again has already assumed homogeneity and isotropy and so on, right? So that line element alone should be enough to derive, together with the Einstein equations, should be enough to derive the effective equation for a of t, correct?
Right, exactly.
Okay, so now my question is, as I see that derivation, what is the version? So there should be some equation that's a double dot, wherever it is, someplace here, you have that version of that thing, which is the a double dot, blah, 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 blah. And the thing that's just surprising to me is the way that c of t occurs in this equation, because this is saying, I'm just very, very surprised that from something where there's essentially polynomial dependence of c of t, that you get something which is logarithmically dependent on c of t. Right, because here, for example, I don't understand how the n here, how did the n, I'm now very confused. Wait a minute. There's two different n's involved here. There's the n, which is the sum over dxi dxj, right? That's summing over dimensions, over integer dimensions, right? And now you've also got an ansatz about how c of t behaves to correct that dimension. But this n here, if I'm not mistaken, is merely the n from the summation over dxi dxj. Is that correct? This is a combinatorial n that you get purely from the summation of those indices.
In integer dimensions, it's combinatorial.
Okay, but so you're making the ansatz then. Are you making the ansatz? So where did c go in this equation?
Well, I mean, c is part of the definition of a.
Okay, but if I change, okay, what you've got here is something, I mean, this is exactly what I was, for my sort of d-dimensional physics compendium, this is exactly the kind of equation I was looking for. That is, this is in a fixed d dimension, ignoring the dynamics of d, or whatever you're calling it, n, whatever, ignoring that dynamics, if you just plop the universe down in 7 dimensions, this is what the FRW equations look like, correct?
Right.
Right. Okay. So now my question is, those equations involve C somehow. I'm trying to understand the interplay because you are saying you can vary the effective dimension by varying C of t. Right? So where does C of t appear in these equations?
Like I say, it appears in the definition of A, and it's coupled with N. But the point is, you can formulate the thing in such a way that you don't actually have to write C explicitly, because you already have all the functions that depend on C.
Okay, so there's implicit, if you lock n and c together, n and c goes like t to the n or whatever. If you lock those two things together, it isn't t to the n, it's t to the, it's
n minus d.
Right. Well, where's d in these equations?
Again, I don't understand what you mean by where is it. I mean, it's...
Well, these equations, okay, if I just plop a universe down in 7 dimensions, the equations that it will satisfy are, if I'm understanding correctly, these equations with n equals 7. Is that true?
But you need there are additional relationships between n, c, d, and alpha, which are needed in order to close this. This system as written is not closed. You need additional, effectively, like constitutive relations that relate n, d, alpha, and c.
No, c is not, and c depends only on alpha, right? C is t to the alpha.
Up to first order, yeah.
Yeah, okay, up to various constants. Multiplicative and additive constants. Okay, but look, so I'm not quite following through these equations because I really would expect there to be some n dots and things like that in these equations. I'm really surprised there aren't any. I mean, maybe they cancel out, I don't know. Because I think you would never see an n dot if you were just saying plop the universe down in 7 dimensions. Right? You wouldn't see the dynamical terms in n. But if they appear through C of t, I can absolutely imagine that there's a time derivative of C of t times something else, which will lead to, n dots, so to speak, in there.
Right. I mean, we've got the same situation as we have with the dimension and the curvature, right? Is that which ones do you treat as fixed and which ones do you treat as varying? The whole point of doing this derivation was to not have to deal with varying dimension and to exchange it all for varying curvature. No,
varying speed of light.
Sorry.
Yeah. Okay, but this claim at the end here, that what's omega sub n?
Well, that's
here.
Yeah.
Oh, okay. That's the n-dimensional
cosmological equation of state parameter.
Right. So for radiation, omega will be 1/3 for 3 dimensions of space, and I think it's 1 over d for d dimensions, because that formula just comes from kinetic theory.
Right.
So omega sub n actually don't understand why. So normally that would be like 1 over n here. Is there a plot of this? Can we plot this? I mean, so there's a lambda here, which again is just a scale parameter, I think, in this equation.
Right.
Okay, so A of t, do you have this formula in some form? Can you get it as a piece of tech or something? Or how do I get this formula without typing it in?
I'll get my working notebooks from 2019.
Because then we can plot this as a function of n. Because again, I think there are some derivative terms missing here. I mean, in other words, I think there's more, but whatever. I mean, this is going to be a decent first approximation.
Okay. Well, I mean, I can rederive the stuff if you think it's wrong.
My guess would be that there will be terms in this differential equation that involve the variation of. But I mean, look, the whole thing is kind of funky because it's making some assumptions about is making assumptions about something we don't understand particularly well.
I mean, obviously there are n dot terms, but your claim is that they appear at second order and below, which
I don't know if that's correct. I don't know. Right? I don't know. Okay, you think that they don't. That's fine.
Well, at least I mean, when I calculated them, they didn't appear. My presumption was that when if one went to higher order gravity, then those terms would appear.
Yeah, but you see, but I think you've got a derivation here, in which n is appearing by virtue of the summation.
Yeah, no, it is absolutely
right, as opposed to it appearing as a result of C of t being manipulated, so to speak.
Why are those different?
Well, because I'm not convinced they have to be the same. That is, you're using C of t as a way to parameterize changing n, and that's a huge leap of faith, so to speak, that you can do that, and that the limits work out correctly.
Why?
Because this is a purely combinatorial way of computing dimension.
It's only you say it's only combinatorial if you make it it's only combinatorial if you set n to be integer.
Well, if you don't set n to be integer, you have no idea what you're doing here.
What do you mean we have no idea what we're doing?
This thing, this formula,
is a tensor projection.
Yeah.
Yeah.
And we don't understand tensors very well outside integer dimension. I mean, we can guess what the continuation is, but it's not self-evident that will work.
That what will work? That you can do tensor projections?
No, that you can do it for d not an integer. Look, it doesn't matter. I'm prepared to believe your formula up to some.
What's all our curvature estimation about? What I mean, so are you claiming that all my functions for doing like tensor calculations are wrong?
No, I'm saying in this particular case where you are parameterizing dimension change using this C of t thing, I think it's a little bit sensitive because you're making two. You're doing two things that are kind of funky. You're essentially continuing this formula, assuming that the summation, assuming you don't have to worry about the explicit combinatorial summation. Fine, that's what we believe.
Nothing specific about that formula. It's a general continuation of tensor calculus, which is kind of the first step in all of this.
I understand. It is unclear to me that interacts properly with assuming that you can parameterize these light cones by saying that essentially what you're doing is to sculpt the edge of the light cone, right? I mean, what you're doing by saying C of t varies like t to the alpha is you're saying, I thought I had a cone, but actually my cone is a thing that, splays out rapidly, right? And that's why my cone is can be thought of as existing in higher dimensional space, because the cone, even in 3 dimensions, for example, my cone, or in let's say 2 dimensions, my cone is, look, what I've got is, instead of the edge of my cone just looking like, plot t as a function of t from, that could be the edge of the cone. I could obviously let's make a more convincing cone. Okay, so there's my cone, right? So what you're saying is your effort to make a space of dimension, let's say, this is what you're doing. You're saying, make my cone be something like this, right? You're spraying out the cone to basically have more space in there, by virtue of the expansion of the cone, so to speak.
I do understand my construction, yeah.
Right. So my point is, it is not obvious to me that plays nice with the idea of this continuation for the summation. But maybe it does. I don't know. It's not so obvious to me.
Well, I mean, this whole formalism is based on this, this proof that so long as one doesn't have a fractal, right, then the generalized tensor projections obey the topological dimension, which is therefore by definition the same as the Hausdorff dimension.
Yeah, I understand. I suspect that there's a certain
it absolutely fails for a fractal, but then our tensor projection things are not well defined for fractals. Actually, no, that's not really true. They are well defined.
Not really true. The basic point is, if the thing has enough, if it's a very regular fractal, you can be unlucky, you can be aligned in some weird direction and it'll go wrong. If you have the thing with some incommensurate slice through the fractal, it'll probably be just fine.
Right. It's so all that's happening. I mean, like if you take the code for doing like curvature tensor projection or something like this, right? In there, I have a documentation example of computing a tensor projection for a Sierpinski sieve graph. All that's happening there is just that the number of effectively independent tensor indices will not be the same as the number of effective dimensions. But that's the only case in which it could conceivably go wrong.
Okay, you sent me this Ritchie curvature estimator. Is that relevant to this? I'm
just saying. I mean, as an example of this general construction of analytically continued tensor calculus. Like I say, I mean, I've got plenty.
Yes, I think that's right. I think it's correct that it. Look, my guess is there's some.
Like in scope, I have examples of computing tensor projections for a Sierpinski sieve graph. All I'm saying is the number of effectively independent tensor indices in that example will not be equal to the Wolfram Hausdorff dimension of the graph. In that case.
Hold on. What are you saying in the scope section? Wow, this is a long basic examples. Okay. Fractional dimensional graphs. Okay. There's a little Sierpinski. Okay. So now you compute this.
Right. So that's a tensor projection.
Which gives a Ritchie curvature of minus 5.5, which is kind of funky.
Right.
Look, I'm sure the reason is because, none of these limiting processes work for something as regular as this. If you align, I'm sure there's a way to do some incommensurate slice with this.
That's absolutely right. I mean, grid graphs are the worst possible cases of manifold. They're the worst approximation to manifolds that you could conceivably construct. Right. Anything regular is bad.
Right. And I mean, qualitatively, the reason it's bad is that to have a notion of, to have something which approximates Euclidean space, there has to be some sense in which there's, homogeneity and isotropy. And a grid graph, actually an interesting point. I mean, if you try and estimate the isotropy of a grid graph, right, you can do that by, something I worked on long, long ago in a field far, far away, of, looking at things like sums of spherical harmonics. No, you're asking the question, how well does this approximate isotropy? And the answer is a grid graph is the worst at giving isotropy. That would be the claim.
Right. It's kind of ironic, actually, that the graphs that produce the most manifold-like, the most manifold-looking objects with respect to the to default graph embedding are the worst manifolds, generally.
Right. I mean, so to estimate the isotropy of a grid graph, what we would do is we would say we could actually compute. My God, I haven't looked at these in a million years, but I think you could just look at, like for example, in a two-dimensional grid graph, you can just say sine n theta. So for every point in the grid graph, right, we could say, so the grid graph, just to give some sense of how this might work. Yeah, I mean, given every embedding, let me think about this. We need angles to make this really work. To estimate isotropy, what would be in our models, how would we estimate it? In our coordinate independent tensors, so to speak, how do we estimate isotropy? I think it involves, the angles involve essentially GD6 going. So you go out in some direction along a GD6, and then you're asking, as you look at another GD6, you're asking about the webbing going from one GD6 to the other, and that gives you an estimate of essentially the angle. And then the question is how you, yeah, so we could probably work out some isotropy measure.
Well, the definition that I used in the papers so far is just the obvious one of, you know, the automorphism, the subgroup of the automorphism group that retains geodesic lengths and origins is maximal.
And that corresponds to isotropy.
Yeah.
So let me think about that. So if you have a subgraph, you make a geodesic ball of radius r, that defines a subgraph. You look at the automorphism group of that subgraph. I have no idea what would lead to that being maximal. Well, what does it mean for the automorphism group to be maximal?
I didn't say the automorphism group. So you look at the automorphism group of the overall graph.
Yes.
Right. You look at the subgroup of that automorphism group that preserves the lengths and origin points of GD6. Okay. And if that subgroup is the whole automorphism group or close to the whole automorphism group, then we say it's, or if it's the whole automorphism group, then the space is perfectly isotropic. The closest, the closer that subgroup is to the whole automorphism group, the more isotropic the space.
I agree that seems like a reasonable definition, but let me think. For the case of the grid graph, the group is whatever D4 or whatever the heck it is. You know, how does that work for the grid graph?
How does what work?
Your construction you just gave. That is, you look at the geodesic ball, which is a diamond in the grid graph. You look at the automorphism group of the whole grid graph, which is it not this D, whatever it is, D, you know, that what's it called? I don't even remember what it's called. The group of the square, whatever it is.
Yeah, dihedral group of.
Oh yeah, dihedral group, right. Okay, so I'm asking, so the automorphism group of the whole space, the whole grid graph, is dihedral group of some order, right, corresponding to the dimension. Now, what is the automorphism group of the geodesic ball that is the diamond? Why isn't it the same? I'm confused. Why isn't that the same dihedral group?
It probably is.
So why doesn't that then, get the gold star for being as isotropic as anything?
I don't know. This is your isotropy estimator. I'm not.
Well, no, I'm quoting your isotropy estimator. We both made the statement that the grid graph is the worst. What's that?
It has nothing to do with geodesic balls.
Okay, so explain your isotropy estimator.
The subgroup of the dihedral group that preserves the length and origin points of GD6 for a grid graph, or for a three-dimensional grid graph, will have 6 elements.
Okay, so your point is you anchor the GD6 to one point. Normally, the collection of GD6 anchored to one point of a given length is a geodesic ball. But what you're saying is you just look at all of those GD6 and you ask, how do those GD6 get transformed to each other? And how do those transformations relate to the possible transformations of the whole space? Is that right?
Right.
So what were you saying about the grid graph?
For a three-dimensional grid graph, it will have 6 elements.
What will have 6 elements?
The subgroup of the automorphism group that preserves the length and origin points of GD6.
And those 6 elements are what? Rotations through 90 degrees and reflections or something?
No, there are 6 possible, if you have a geodesic of length L, originating at point X, there are only 6 possible directions that geodesic could also have been projected in and still remain the same. Right?
Well, can we do the two-dimensional case? Because that's easier for me to understand. Is it 4 in that case?
Yes.
Okay, because basically if I have a grid graph, I make a random grid graph here, and I start a geodesic here, right? The geodesic can go happily along here, right, to this point. So now the transformation that you're describing will end up with the geodesic going here, right? Is that correct? Okay, so I don't understand why the transformations on the geodesics, of which there are 4 possible geodesics you get.
Yeah.
Help me out with why that's different. Go ahead, what were you going to say?
Right, so the subgroup has order 4.
Yes.
The dihedral group of order 4 has 8 elements. So
because it has reflections and things as well. And
right.
it has, for example, the flipping along the sac. Well, that thing already had which elements of the dihedral group, of the full dihedral group of the grid, are not present in the symmetry group of the geodesics?
Well, everything that isn't a rotation. Right.
So you mean the flips?
Well, there's the identity map, and there are the 3 rotations. Those are all present. Then there are the X and Y reflections, and then there are the 2 diagonal reflections.
Yeah, okay.
Missing, because if you attempted to do a diagonal reflection or an X and Y reflection, you would end up with either you end up with a degeneracy, or you end up with a geodesic that's actually longer with respect to the grid graph metric than the original geodesic you started from. So when we say the grid graph is not very well, not a good approximation to an isotropic space, that's a consequence of the fact that the subgroup of the automorphism group that preserves length and origin points of geodesics is half the size of the actual automorphism group.
Okay.
But for a cube, it's even worse.
Right? Yeah, I get it. Okay, so the basic point is
48 isometries, I think.
Right. So the basic point is that while geodesics are preserved by rotations, the whole space also has reflections. And I suppose, yeah, it's not obvious to me. I mean, it's not self-evident that this is the actual worst case, but that would be interesting to work out. But the main thing here,
I suspect it's close.
What's that?
I suspect it's close.
Yeah. Let's see. All right. So just for a moment, and then I want to just cover a few other things, and we should wrap up. But basically, the thing I'm trying to understand here is this equation, if it has all the terms it needs to have, and let's assume it does, while we don't know what n of t is, I mean, this equation, this should be n of t, correct? This is a double dot of t. That should be n of t, right? If we're going to write it out explicitly. Okay, but in this equation, is it still n of t, or is it n a constant in this equation?
Well, the point of doing this formalization is so that n can be treated as a constant, because all of the dynamics is shifted onto c.
But where is c in this equation?
Well, in the definition of A.
Okay. Did you by any chance have a version of this equation that I can just run?
I was looking for it, but I mean, these notebooks are kind of a mess. I wasn't.
Yeah, I know. You were not well equipped to do this. You know what? If you can just that tech fragment, is it easy for you to just pull out the tech fragment, because we can just import the tech fragment?
Potentially. Let me have a look.
I would just go to the text source and search for Hollander and Pereira.
Right, but first I have to pull the text source from my other hard drive.
I hope you've backed up all your stuff, Jonathan.
Yeah. It's just that normally the only stuff I store locally is the stuff that's been done in like the last year. I don't usually store things from more than a year ago.
Yeah, well, you don't have to worry about the multi-decade yet. I'm working on the storage media have long died model. The human is still around, but the storage media are long gone. Anyway, I'm curious. Did you in fact try plotting this out and seeing what it does and things?
No, I didn't.
Okay, so I want to do this. I'm excited.
Okay. You might have to vamp for a moment while I extract things.
Okay. Well, let's look at some comments on the live stream here. Sorry. Somebody was commenting. Church was commenting. Time is a dimension. Dimensions don't change with time. No. Time isn't a dimension. That is a mistake that was made in 20th century physics. They're probably courtesy of Hermann Minkowski, who was very pleased with the fact that you could represent space-time just like the quadratic forms that he'd studied in the theory in number theory. And that led to people saying, oh, look, time enters just like space in all these equations. Time must be just like space and just a dimension like space. One of the key things in our models is that that's not how it works. Time is kind of the inexorable progress of computation that computes new states of the universe from old ones, and space is just a feature of essentially the data structure that represents the structure of the universe. And the fact that those two things are different is incredibly key to our models. And you say, but how can that possibly be right? Because relativity implies that they behave in somewhat the same way. Well, the whole point is that that emerges in our models as a result of this whole structure of causal graphs and causal invariance and all this kind of thing, that on the large scale limit, you get relativistic behavior, even though space and time are of a completely different character at an underlying level. And so dimension that we're talking about here is spatial dimension. The dimension of time is always, in some sense, one, because in a sense, what's happening is that there is a progress of time that's happening by this sort of, and by the way, if you said there was more than one dimension of time, you would be saying, in a sense, there's more than one way to make computational progress. And that, as you work that through in our models, you'll end up finding that if there was more than one way, there effectively are event horizons where you're independently progressing time on different sides of the event horizon, which is something perfectly reasonable to do, but is not what sort of our experience is. And actually, recently, I've been sort of trying to understand how consciousness works in all of this. And there, it's a key fact that we have this kind of one-dimensional thread of experience. And that's associated with this fact that time is kind of this progressive computation type thing. Let's see. Bob is commenting, we need a widget to rotate in more than 3 dimensions. Yes, I agree. Actually, a long-time user of ours, Andy Hansen, has developed all kinds of interesting things for rotating in 4 dimensions, and I should really understand what he's done in more detail. I have a hard enough time visualizing things in 3 dimensions, let alone 4. So I suppose maybe I'm prejudiced to say there's got to be another way to do it, because actually we've had a number of things. Maybe we even have some in the function repository that are like the 120 cell, which is the regular polytope in 4 dimensions. Visualizing that and looking at its projections as you turn it around. Yeah, I just don't. Actually, it's a very interesting case now that I think about it. We talk about the integration of experience to make a notion of space. The corresponding thing in 4 dimensions, it's sort of interesting to see what that actually is like. I wonder what happens. Let's see. Do we have the, let's see, 120 cell. Let's see if that, there we go. There's a graph. Great. There's a unit. Okay, so there's its graph. So let's say graph data. Come on, there we go. Okay, so that's the 120 cell. So that is to be compared with, I don't know why its vertices are so big. So that's a four-dimensional object. So if I were to look at the, let's say the dodecahedral graph, it's Nick is observing that his machine learning models on GPUs experience multidimensional time. Because they effectively have event horizons in them. So okay, so this is a approximation to a this is a dodecahedral graph, and if we say graph 3D of that, well, oh come on, that's really lame, if I might say so. That's really lame. Why is that flat? Okay, let's say graph layout goes to spherical embedding. I'm going to complain about this. Why isn't that making a nice dodecahedron? Why is it still flat like that? It's very odd. Well, maybe actually, hold on a second. Maybe I've got a problem here that graph 3D of, let's say, edge list of %8, just to get rid of any possible, there we go. So why did it do that? Okay, so the graph data, the actual dodecahedral graph was burnt in as being flat. But if we allow it to just auto, okay, so then this here, line 7, should be graph 3D of, let's say, edge list of line 7. Okay, so that's 120 cell. And this is the three-dimensional projection. Yeah, I see Jonathan has this thing. So that's the three-dimensional projection of a four-dimensional polytope. I don't know what's going on here. But and Jonathan, if you're back with us, this is sort of interesting because we've been trying to understand what would it feel like to have sort of a different rule reference frame, a different way of integrating elements in the universe. And we know in some sense, this thing here is absolutely, there's a nice uniform way to understand it. It's kind of like a little bit of this 120 cell in four-dimensional space is kind of like the dodecahedron in three-dimensional space. This has constant distances and things like this. But yet here, projected into what our experience allows us to understand, boy, what a mess. And I suppose that's interesting. Okay, so here's another interesting point, that because we exist, so there's a good point. There's a good example of where our particular sensory and experience information is really, really locked into three dimensions. So it's hard for us to understand these things in four dimensions. But if we lived at a different stage in the history of the universe, if the universe has dimension cool down, we would expect that our it would be, we would have a very different experience of this. Anyway, okay. I'm just going to look at from William here. Space is a discrete number of different objects with certain sizes, also limited. Yes, thus number of conceivable particles of a particular energy scale is limited. Yes, I agree. Yes, the only problem is that, in our models, the number of atoms of space in your average electron is around 10 to the 30th. So it's hard to see discretization effects. I mean, that's an interesting question, actually. Okay, that's an interesting question. If you are able, okay, this is an interesting idea. So, okay, so just, I'm very disorganized here, but this, okay, this is actually an interesting idea. Okay, hold on. Okay, so this is experiment 04. Okay, so the question is every photon the same? Okay, So let's imagine that they are topological defects of some kind. And then the question is, if each photon corresponds to some so Jonathan, you get the point here. I mean, so we're saying each photon is like some, topological obstruction in space-time. Okay, the idea is, could you tell? Okay, the question is, in a coherent collection of photons, could you tell non-identicalness in some sense of the photons? So in particular, I don't think I've ever worked this out. In a typical laser, for example, let's say we have a laser, I don't know, maybe I'm out of date, but how many photons are there in a typical pulse from a typical pulsed laser? I actually don't know. Should know that. I'm going to guess it's certainly in the trillions, if not more. And my question is there any way of telling sort of non-identicalness of those photons? Anyway, but let's look at your variable speed of light thing, and then we'll probably have to wrap up soon. Okay, so you've got a thing here, and it is yes, I do want to escape them. Okay, here we go. Although, actually, why don't I do this? Control $, and then paste that. If this works, it will be magic. Well, that's not very nice. Claims that the syntax, okay, so import string of that, comma, tech. Didn't like it. Okay, what's wrong with this formula? Can you see that at all? Well, let's start editing it, I guess. Oh boy. You know what? This is a silly thing. Let's just type it in. We know how to type. N times n minus 1 over, well, I'm just going to leave out, shall I put in the lambda? I guess I can put in the lambda. To the power 1 over n times, I'm going to replace omega sub n by 1 over n because I think it's the right thing to do. Times exponential of 1 over n plus 1 times the square root of 2 lambda n over n minus 1 times t. And I don't think I want that. All to the power 2 over n times 1 over n plus 1, all divided by e to the square root of 2 lambda over n times n minus 1. Okay, there we go. All right. So
are you not missing a -1 in the exponent in the numerator?
Yeah, that's why I started using computers for this kind of stuff, is because I never got those kinds of things right. Okay, let's see. Any other mistakes?
No, I think that looks good.
Okay, All right, so now let's say with lambda equals, should we say lambda equals 1, or what value of lambda should we pick?
Yeah, why not?
And what do we do? So n, we imagine here. So this we want to do as a function of n and t, right? So the most naive thing to do would be a plot 3D of this, of this thing here, which is kind of a messy object. And I don't know what scales it has in it. But this thing as a function of n, let's say varying from 1 to 5, and as a function of t varying from 0 to 10. And I have no idea what I'm going to get here. Okay. Dandy. So let's look at this thing as a function of t. Well, as a function, let's look at its n dependence here. Let's look at its power series around n equals, let's say, n around 1 to third order. What an absolute mess. Oh, it's got exponential scales in it. Forget it. Can't be done. Okay. So let's see what this formula is in the case where, let's at least look at the formula for n equals table as n goes from 1 to 4. Okay, so let's just do a full simplify. Okay, so it's not very happy when n equals 1, but let's try this. Okay, pretty weird formulae here. So as a function of, as a function here, what we've got is this is dominated by e to the 3. So let's look at the asymptotics of these. Oh, come on. Come on. Why doesn't it give anything specific for the asymptotics of these? I don't understand. Wonder whether I have to map it over this, but I can't see why I would have to do that. Did I get this wrong? Are those can't be the asymptotic forms of these? Okay, the limit, I can see that the limit as t goes to infinity, it doesn't care about the e to the minus. Oh, it does, doesn't it? Oh boy, this is a complicated mess. Okay, but so let's look at these things as a function. So rest of this as a function of, so with lambda equals 1, what happened here? What happened here? Why did it not replace lambda? Did I forget to put parens around the denominators here? Jonathan, are you still with us?
Yeah, sorry, I was working. What's going on?
Well, have you been paying attention to this? Did I get this wrong?
Looks okay to me.
Okay, so let's go back down here. Why is with lambda equals 1 not working here?
You already did with lambda equals 1.
But where's the lambda? No, I didn't. There's still, I put back the lambdas in here. Okay, so here, I'm very confused why that with didn't get rid of the lambdas there. What the heck is going on there? Okay, so let's now look. Let's see whether asymptotic can do anything useful with this. Okay, that's more like it. Okay, so look at this behavior as a function of your n, as a function of dimension. It's e to the t over square root of 3, e to the minus. That's just freaking weird. Oh, times this. Okay, so if we look at these things, if we say plot those, t goes from 0 to 5 or something. Okay, so these gets progressively less extreme, right? Is that what you would expect? These expansion rates, Jonathan, are you still with us?
Yeah.
So as d increases, the expansion rate gets smaller. Is that what you would expect?
Right.
Why is that obvious? So this is the formula for a of t. So that's saying as the dimension gets bigger,
the scale factor grows more slowly.
and is that obvious?
I don't know. I mean, is it obvious that the volume element is dominated to first order by an exponent in dimension? Yeah, probably.
Volume element exponent in time here, that this is growing exponentially, but the exponent appears to be 2, 3, and then here, it's a weird function, right? So I mean, here, if I do the corresponding thing, and again, I'm very, very confused by the fact that with lambda equals 1 isn't working, and I don't understand why. Maybe let's just try it here. Okay, I don't know why it didn't work before. Okay, so let's say n goes from 2 to 10, for example, and then let's do a plot of that from t goes from 0 to 5, and let's do an evaluate in there just for good measure. Oh, look at that funny thing. Interesting. Okay, so then let's say n here. So let's say I think if we say labeled with n there, do I want to say call out? Oh, I put it in the wrong place. Table of labeled of that, comma n, comma this. Oh, that didn't help. Let's say call out instead. Okay, so this is showing, oh, we cut off that, just a second. Plot. Okay, there we go. Okay, so this is showing as the dimension increases, the growth rate of A of t decreases.
Yeah, obviously.
Why is that obvious?
What do you mean? Like I said, isn't it obvious that the first order term in the expansion rate of the volume element is exponential?
Yes, but why is the exponent decreasing as the dimension increases? Because that's what we're seeing here.
Yeah, I completely don't understand. So wait, so A of t is the conversion factor between the proper time in the co-moving frame and the proper time in the physical frame, right?
Yep.
So the dependence of the volume element on A is exponential, right?
Yes.
we have a differential equation that is changing the volume element by a certain amount. So one would expect A to increase less rapidly as the dimension gets larger, because the leading order term in the expansion of the volume element is exponential. What?
It may be obvious. Let me think. Okay, so hold on.
I increase a sphere of radius n by a constant volume per unit time, and I look at what's the, and I look at the growth rate in the radius as a function of dimension. That radius will grow less rapidly in higher dimensions because the leading order term in the volume element is exponential.
Right. So for a given volume, for a given sphere volume, the rate of growth of radius needs to be less in order to achieve a given overall volume increase.
Right. What am I missing? This is just...
Yeah, that's fairly obvious, right? And then, so that means that for a sphere, right? So to achieve the volume of the sphere is r to the d times some various constant factors, right? So it's basically the volume, it's the region measure of a ball of, I need to remember how this works. How do you get a ball of dimension? How do you get a hypersphere? How do you get a ball of dimension? Oh, I know what it is. Centered on point P. So we just want table. Oh, this is kind of hacky. Of 0, comma. It only does it for, oh gosh. How do we get the volume of a d-dimensional thing with arbitrary d? Yuck. Oops. Yeah, so this should give us 1, pi d up to 6 or something. Okay, there we go. So those are the constant terms, and now that's something with gamma functions or whatever, and it's r to the d. The volume goes up like r to the d. So for a given volume growth rate, we expect that the radius is the 1 over dth, is the dth root of that. So that makes sense. Okay, I'm happy. Yes, I agree.
I'm confused. What was the question?
The question was why this plot looks like this, and I now think I understand roughly why this plot looks like this.
But isn't it just because the leading order term in the expansion of the volume element is exponential? The Friedmann equations depend on volumetric density. So obviously it's going to decrease. The rate of expansion is going to decrease in higher dimensions. What?
Yes, I'm simply, okay. Yes, the argument is basically to increase this expansion rate, A of t, for a given volume element, which is A of t to the power n, basically, right? A of t to the power n. So if I were to look at this picture here, that's
I understand the argument. I'm asking what's the confusion? That's
because it takes me a while to understand anything. Okay, so the claim would be if I look at this to the power n, this thing here to the power n, very nice. They're all basically more or less the same up to a sort of constant factor. Right?
Well, yeah.
Okay, good. I'm just checking that it makes sense.
The equations are a volumetric density equation. I mean, that's how it works.
Volumetric density that depends on the that depends on this right-hand side.
Right. So the infinitesimal change in A is dependent on volume, but A is dependent on the nth root of volume.
Yes. Okay. Well, it was, as usual, you were quicker than me at understanding that, but I think that's correct. Okay. So again, I mean, the question here, and just trying to wrap this up for now, if we have this cool down phase, then there may be some effective, generalized Friedman, Robertson, Walker, which you've got some piece of here, that, and the question would be, for example, if you have a density perturbation in that, what happens to that density perturbation? How does that density perturbation compare to the density perturbation you get in the standard FRW situation? And for example, there's a very detailed calculation of the spectrum of density fluctuations, in the early universe leading to temperature inhomogeneities in the cosmic microwave background. And the question is whether this would imply a different spectrum of those density perturbations.
Right. Yeah, it's a very interesting question. It'd be very cool if we can get to the point where we can actually compute angular power spectra and things.
Right. Because there's some kind of Gaussian noise, but that Gaussian, my guess would be, and I haven't followed inflation since 1978 when I last worked on it. So I'm embarrassingly out of date, but I would assume, different regions of the universe, if they have a different T0s, basically, will have dramatically different amounts of expansion in standard inflation scenarios. But okay. So the question is to compute the spectrum of density perturbations, which might be different, probably would be different. Because this scenario is not, this scenario is inflation. Okay, so I think I'm finally understanding. This is inflation in the sense that there are exponentials involved, but the exponentials have a completely different origin from the ones in inflation. Is it a different origin? What is the trade-off between exponential expansion rate? No, it's a different thing. Okay.
I don't understand why it's different.
Exponential expansion rate versus dimension change.
Well, it's hard to define what you mean by exponential expansion. I just meant the standard inflationary model, right? If you look at what is the conformal structure of a standard inflationary solution, all that it's doing is it's pushing back the initial curvature singularity to minus infinity conformal time, right? That's kind of that's the
right.
Inflation. And isn't that exactly what we're doing with a dimension change?
Is it? So, okay, so if you look at the causal graph, you're saying, can we think about the pushing back of the initial singularity through as being, explain that to me. So you're saying that dimension change, you think, has some equivalence to inflation.
Well, I showed in the paper that the conformal structure is equivalent, and when you think about it, it's really obvious that should be so. I think, isn't it? Because okay. So let's define a distinguished point in the causal evolution which is kind of the point where the lambda CDM model takes over, right? That's our zero in conformal time.
Okay.
So by having a preceding infinite dimensional region, what we're doing is we're adding an arbitrary number of causal edges prior to the zero of conformal time.
Yep.
Right. And so in the limit, as the number of causal edges goes to infinity, that means our initial curvature singularity, which for us is just the initial hypergraph, gets pushed back to minus infinity conformal time.
Well, you're saying to have higher dimensions, the definition of that is that you have more events, basically. And you're saying,
not just more events. It's because you could have loads of events but only but ones that separated two immediately neighboring space-like hypersurfaces. What matters is event density with respect to the trade-off between proper time and conformal time.
Yes.
Right. So the point is that if you look at that, in higher dimensions, you must traverse a larger number of intermediate space-like hypersurfaces in order to achieve the same proper time distance.
Okay, let's just walk through that for 1 second. So if we have a causal graph, let's say we have an exponential causal graph.
Why?
Because it's just a model for what we're talking about. But maybe we don't need that. We can have okay, what you're saying is, let me just understand the definitions here. So you say proper time okay, help me unconfuse myself. So the proper time in the cosmological rest frame, what is the relationship between the proper time and the sequence of updates? We have a sequence of events, and we look at things in the cosmological rest frame, and we just count the number of slices in foliation in the cosmological rest frame. And that gives us proper time. Is that right? Or am I confused?
I don't really understand the setup.
Our standard causal graph, as drawn in a layered embedding.
Yeah.
Proper time is the number of layers in that layered embedding, is it not?
With respect to an observer in geodesic normal coordinates localized to that hypersurface.
Yes. Right. As like the cosmological rest frame, for example. Okay, so then if that's so what you're saying is if we have a causal graph whose effective dimension is large, yeah, I'm confused here. I mean, I'm okay. Okay, the interesting claim here, which perhaps you've been saying it for ages, but I didn't internalize it, is that in some sense, dimension change, the usual trade-off between dimension and curvature, you claim, becomes extreme for the case of exponential expansion.
Right.
And that therefore there is a way of thinking about, whereas normally it is not worth trading off dimension for curvature, so to speak, that maybe in the case of inflation it is, and that inflation is best thought about in terms of dimension change as opposed to curvature. Is that what you're claiming?
It may be a corollary of what I'm claiming something much, much simpler.
Okay.
Which is just that the conformal structure of the two solutions is the same. I mean, for very obvious, right? If we want to compute co-moving distances from which we can then compute conformal times, those co-moving distances are defined with respect to a volume element that is now higher dimensional. So we're integrating over the reciprocal of a higher dimensional volume element, i.e. one that scales more rapidly.
Yes.
So then the trade-off, the exchange between conformal time, the ratio of conformal time to proper time gets larger as the dimension increases.
Yeah, I agree with that. Yes, I agree with that.
And therefore, it's not just about adding more causal edges. It's crucially also that you're stretching out the number of intermediate space-like hypersurfaces between two instants of proper time. And so if you take the limit of that process, as you make the spatial hypergraph arbitrarily high dimension.
I see. So to say it a different way, if you've got just more events there, and as you foliate that thing, if you want to have a fixed number of events per slice, the number of slices has to get larger.
Right, so something like that, yes.
And therefore you're pushing that with respect to the slices, that you're just packing in more and more slices, which is otherwise known as pushing back the origin with respect to your measured time.
Right, but yeah, it's specifically with respect to conformal time. And so you end up with a space-time that is conformally equivalent to an inflationary space-time.
Well, that's an interesting claim. I mean, so that would be a claim that's a very interesting claim, which I don't think at least I've not internalized before. The claim that the infinite dimensional cooldown model is in some sense equivalent to some kind of inflationary model. And not just because I had thought it was a different thing. I mean, I thought since the time of NKS, I think I discussed this in the NKS book as being a scenario that would give the same kind of homogeneity results, but quotes for a different reason than normal inflation. So this is claiming that it's actually the same reason in some sense, that the difference is you can't formulate, whereas ordinary inflation. Okay, so just to walk through this. So what you're saying is ordinary inflation is fixed to 3+1 dimensional space, but has extreme curvature. And in this case, we're trading off that curvature. We could say it's flat for all we care, but we're trading it off for changing dimension, which is outside of the usual. Well, so here's an example of a difference. So because we can have topology change, kind of cheap topology change, you can end up with regions, as we saw in those initial things we looked at, you can readily end up with regions of the universe that break off. Right? So there will be a question, if in the early universe, in the kind of cool down phase, pieces of the universe broke off, what observable consequences might that have today? Well, anyway, I think, the question is, if we can get, if you're right that this variable speed of light thing is an adequate parameterization of changing dimension, then this cosmological perturbation theory thing might be enough to give us, to tell us in the case where we include that variation, what does that do to the perturbations in the cosmic microwave background? It probably doesn't help that there's an additional parameter. Although maybe there already are boatloads of parameters in standard inflationary models. Again, I haven't looked at these things in 43 years, so I'm right. Severely out of date. It's probably
there are a lot. For like, parameters. For scalar field inflation models, the kind that come from like supergravity and things, you regularly get like 14, 15 free parameters. I remember discussing with Max the model he was working on for his PhD, and I think it had 14 parameters in it. And
oh God. Well, okay, so we need to wheel Max back into this picture, so long as he doesn't rebel having to look at inflationary scenarios, universe scenarios again.
Right. I think we both agreed in the end that the model he was working on was kind of, at least free of any real predictive power, because it was so unconstrained.
Well, quite. But the question is whether we can get something. I wonder so here's a question. I mean, in the space of inflationary universe models, does the particular origin, see, the problem is you just throw in random fields and you say that they're yeah, I mean, does is it, can we narrow down the parameters of an inflationary model by saying that it is a result of dimension cooldown?
Right. I had a winter school project on that topic, but no one took it up.
Fair enough.
But we have all the pieces in place, right? We can define we now have code that defines a coupled scalar field to gravity, a massive scalar field to gravity. With that, you can then do cosmological perturbation theory, and you can just start off one of these evolutions from an initial hypersurface with infinite dimensions.
Yes. All right, very interesting. Well, we got only about 1% of the way through what I'd hoped to talk about. but this was interesting. I am somewhat curious about this thing that seemed kind of crazy about, you know, the are all photons the same question, and whether there might be some way to tease out, even if there's a difference, if you have enough photons, is there a way? I mean, it's a very weird question, like many of these things. I mean, the kinds of measurements that we're going to be able to suggest are mostly pretty weird things, that mostly are things that have never been measured before. And that's always it's like, think ether drift. Nobody had bothered to measure that before there was a reason to measure it. And similarly, your average dark matter experiment, there are things people are measuring that nobody bothered to measure before. So I think we're still what we have to identify is those kinds of things. But we ran way out over time, and we should probably wrap it up. And well, as always, a fine conversation, and to be continued. All right, and I got a chance to read a section of your paper, which is always good. All right, okay.